Let's continue looking at the energetics of forming ionic compounds by looking at what we call the Born-Haber cycle. The Born-Haber cycle, for sodium chloride, using that as an example, is just an application of Hess's law. We're going to look at different equations that we can add up to show where the energy of formation comes from. So the first equation that we're going to look at, chemical equation, is forming gas phase sodium atoms from solid. That costs us the heat of formation for forming gas phase. Again, kind of like heating ice and getting it into gas phase, you have to put energy in to do that. Another equation that is related is the formation of monatomic chlorine from its ordinary standard state of diatomic chlorine. We can add on the ionization energy for sodium. So we're going to take this gas phase atom, use that as a reactant, and rip an electron off to form the sodium ion in the gas phase. By definition, having those both gas phase, that's our ionization energy for sodium. Then we can take that electron that we've taken away from the sodium atom and add it on to our gas phase chlorine atom to form a gas phase chloride ion, and this is our definition of what we mean by an electron affinity. And then finally, let me introduce the lattice energy. Notice I have a minus sign here. That's very important. This is minus the lattice energy. If you take a gas phase sodium ion and a gas phase chloride ion and let them combine to form a solid state sodium chloride, that is, by definition, minus the lattice energy for sodium chloride. And I'll come back and more carefully define this in just a bit. But here's the point. If we add these equations together, we'll see that they add to give us our formation reaction. Now let me just go through and cancel things out that appear on both sides. Sodium in the gas phase is on the right in the first equation and on the left in the third equation. Those cancel. And let's see, chlorine gas is on the right in the second equation, on the left in the fourth equation. Those cancel. The electron removed from the sodium is used by the chlorine, so the electrons are on both sides. That cancels. The sodium ion itself in the gas phase cancels with the sodium ion on the left-hand side of the minus lattice energy equation. The chloride on the right in the fourth equation cancels with the chloride on the left, and we are left with our formation reaction, so that if we add together by Hess's law all of these energies, it should give us the heat of formation for sodium chloride. So let's back up and define the lattice energy a little bit more carefully here. By lattice energy, we mean the energy required to separate 1 mole, that's important, 1 mole, of ionic solid into gas phase ions. So this is the defining equation for a lattice energy for sodium chloride. It would look different for different substances depending on how many ions are present. So the heat of reaction for this reaction, notice the phases are important. That is what we mean by lattice energy. This is exactly the reverse of that last equation that I had on the previous slide. That's why we used minus the lattice energy on that slide. So if we set up our Hess's law, we know that the heat of formation for sodium chloride can be written as the sum of those various equations on the previous slide, and using the numerical values for the heat. So we've got the heat of formation of sodium gas plus the heat of formation of chlorine monatomic gas, plus the ionization energy for sodium, plus the electron affinity for chlorine, minus, because we have the reversed equation, the lattice energy. Now this is actually what we want to get our hands on, because we can look up all of these values in black in the back of the book or in the chapter itself. So let me just rearrange this equation and solve for what I've highlighted in blue, the lattice energy. So we move the lattice energy from the right-hand side of the equation over to the left, change its sign. We subtract heat of formation of sodium chloride for both sides. That gives us a minus delta HF sodium chloride on this side. And now everything on the right-hand side in this equation we can look up numerical values for and calculate the lattice energy. And here they are. These are all values in kilojoules per mole. Heat of formation of sodium in the gas phase, you can look at that up in Appendix C, 107.7 kilojoules per mole. Heat of formation of monatomic chlorine gas, 121.7. That's all about breaking that bond in the diatomic chlorine. Ionization energy of sodium, we saw in this last chapter, is 496 kilojoules per mole. That was in chapter 7 in a table. The electron affinity of chlorine is minus 349 kilojoules per mole. And then finally, we can look up the heat of formation of sodium chloride. In Appendix C, it's minus 410.9 kilojoules per mole, and we subtract that. Adding all of those numbers up, we get 787 kilojoules per mole as the lattice energy for sodium chloride. Thinking about this being subtracted up here, that explains why the heat of formation of sodium chloride is so exothermic, because we end up subtracting 787 kilojoules per mole, and that's why the heat of formation of sodium chloride itself ends up being negative and hence exothermic due to the energy released when those gas phase ions coalesce and form solid sodium chloride. Now let's think about where this energy comes from in terms of the individual particles in the lattice. So here's sort of a graphical representation of the Hess's law. Here's our, let me just outline this. Here's our starting material right there. So there's sodium in the solid state and chlorine in its standard state. If we add energy, we can convert the sodium solid to a sodium gas. Add more energy, we can break the bond and form monatomic chlorine. Add a big chunk of energy and we can rip that electron off the sodium and form sodium ion. Then take that electron and stick it on the chlorine atom to form chloride. Remember, that gives off energy as an electron affinity. And then finally, that minus the lattice energy takes us way down to this energy that's much below where we started, hence an exothermic reaction. So the lattice energy, the origin of the lattice energy in terms of the individual particles, is that it's a sum over all attractions between all pairs of ions. And in fact, let me just be a little bit more careful here. It's the sum of all attractions and repulsions between all pairs of ions. So positive ions repel positive ions, but they attract negative ions. If we add up all of those energetic interactions, we get, using Coulomb's law, this is the interaction between two ions, ion 1 with a charge Q1, ion 2 with a charge Q2, separated by a distance between ions 1 and 2, R12, and this is just some constants. Don't worry about the value of this constant for now. We're not going to use this equation to calculate anything. We're using it to understand sort of what makes lattice energy bigger or smaller. And in fact, the book uses just a kappa there to combine the 1 over 4 pi epsilon 0. Again, the value of this constant is not important for our use. Now what we want to do is add up all of those attractions over all pairs of ions I and J. So this bit of notation, which looks maybe a little bit intimidating, simply means add up all of these energies over all unique pairs of ions. And the I not equal to J just means we don't pick the same pair twice. So we're not looking at the interaction of ion 1 with ion 37 and then again looking at the interaction between ion 37 and ion 1. We just use one of those. So add up over all of the ions this interaction. And the point of this, again, we're not going to use this to calculate anything, but it is useful to make some simple predictions about the relative sizes of lattice energies. It tells us, look, we've got products of ions in the numerator. The bigger that product of ions, the larger the lattice energy is going to be. So if I have a +2, -2 pair of ions, that's going to lead to a larger lattice energy than if I have a +1, -1 pair of ions. And similarly, because the distance between the ions is in the denominator, the smaller the distance, the bigger the lattice energy. And how does that distance get small? Well, if the ions themselves are small and can get close together, then you'll have a smaller distance. So we can use that to predict that smaller ions will have a larger lattice energy. So I've summarized that here. Based on the form of Coulomb's law, we expect a larger lattice energy for ionic substances with bigger charges because of the product of charges in the numerator. We expect a smaller lattice energy for ionic substances that have larger ions because they can't get as close to each other. And if we look at the second one in particular, the first one's the most important. We're going to look at that too. But let's look at this smaller effect. There's some examples in the book that show for ionic substances where the product of the charges is the same. These are all +1, -1 ionic substances. If you look at increasing cation radius using our trend in cation sizes, this is where we apply those trends, we see that the lattice energy gets smaller for larger cations. And if we look at the anions and keep the cation constant, again, these are all +1, -1 ionic substances. As the anions get bigger, the lattice energy gets smaller, exactly as we would have predicted by looking at Coulomb's law. Finally, and even more importantly, if you look at the product of the charges of the cation and anion, that plays an even more prominent role in predicting lattice energy. All of these ionic substances have +1 cations and -1 anions, so that the product of their charges is 1, the magnitude of the product of the charges. The differences between the energies here have to do with the sizes of the cations and anions. But look at what happens when we go to a +2, -1 ionic compound. Look at how much larger this lattice energy is. And finally, here's a +2, -2. The product of those charges is 4. And it's much larger than these lattice energies. And this last example, this is a +3, -3. So the product is 9, and you can see that the lattice energy, again, increases by a large amount. So if I look at, for example, the magnitude of Q1 times Q2, and just fill in the table here, here it's 2, 2, 4, 4, 4, and 9. And we would expect the lattice energy to increase with an increase in that product of charges. And it does.